Okay, so dito na tayo sa multi-pressure system. So sa picture na to, makikita nyo yung dalawang ano siya, pressure, high pressure and low pressure. So ito yung lowest, 1, 2, yung numbering nyo, okay? Ito yung standard compression, meron condenser and evaporator. In between, meron tayong staging ng compressor. So meron din heat exchanger dito and flash chamber. Okay? Dito natin ma-explain yan sa ibang slide. Yan. So, multi-pressure system in industrial refrigeration. Commonly application ito is yung sa industrial. A multi-pressure system is a refrigeration system that has two or more low side pressure. The low side pressure is the pressure of the refrigerant between the expansion valve and the intake of the compressor. A multi-pressure system is distinguished from the single pressure system which has but one low side pressure. Kasi many times na dalawa ang temperature mo, evaporating temperature mo. So ito ang pwede. So a multi-pressure system may be found, for example, in a dairy where one evaporator operates at negative 35°C to harden ice cream while another evaporator operates at 2°C to cool the milk. Another typical application might be in a process industry where a 2 or 3-stage compression arrangement serves as an evaporator operating at a low temperature of negative 20 or lower. So ito sa internet lang ito. So ito yung diagram. So ito yung isang evaporator, warmer, and isang mas malamig. So yung compression mo, so dito, sa either isang compressor to, so dalawa yung evaporator, expansion valve and evaporator. Then mag-merge na lang doon. Okay. So removal of flash gas. So a saving in the power requirement of a refrigeration system results if the flash gas that developed in the throttling process between the condenser and evaporator is removed and recompressed before complete expansion. So, figure 1. When saturated liquid expands through an expansion valve, dito, yan, the fraction of vapor of flash gas increases. The expansion process shown on the pressure enthalpy diagram, figure 1, takes place from 1 to 2. The stage point, as the expansion proceeds, moves into a region of greater fraction of vapor. Ito yung walang flash gas. The end point of the expansion 2 could have been achieved by interrupting the expansion at 3 and separating the liquid vapor phase, the liquid and vapor phase which are 4 and 6. So dito sa 3, interrupt siya. So 4 and 6, hiniwala yung vapor sa liquid. The expansion could then continue by expanding 4 and the vapor 6 to the final pressure, giving 5, 7. The combination of the refrigerant at the state 5 and 7 gives 0.2. So ganun din. So ito yung diagram, flush tank for removing flash gas during expansion process. So dito, sa expansion, pasok ito sa 3, then maghihiwalay siya. So 4, kailangan mo ng expansion valve, papunta sa evaporator. So ito, papunta sa compressor. Inspection of the expansion 6 to 7 confirms that it is wasteful. In the first place, the refrigerant at 7 can do no refrigerating. So in the second place, work will be required to compress the vapor back to the pressure it had at 6. Why not perform part of the expansion, separate the liquid from the vapor, continue expanding the liquid, and recompress the vapor without further expansion? The equipment to achieve this separation is called the plus tank, figure 2. The expansion from 1 to 3 takes place through a float valve, which serves a further purpose, the further purpose of maintaining constant level in the plus tank. To recompress the vapor at 6, a compressor must be available with a suction pressure at 6. Thus, 2 compressors are needed in the system. The plus tank must separate liquid refrigerant from vapor. The separation occurs when the upward velocity of the vapor is low enough for the liquid particles to drop in the tank. Normally, vapor velocities less than 1 meter per second will provide adequate separation. This velocity is found by dividing the volume flow of the vapor by the surface of the liquid. Now, the most efficient way to remove plus gas would be to separate the vapor continuously as it forms and to recompress it immediately. No practical means has been developed to accomplish this. Intercooling. Ito yung mga sa staging. Sa multi-stage. Intercooling. Between two stages of compression reduces the work of compression per kilogram of vapor. In two-stage compression of air, for example, an intercooling from 2 to 4, ito yung compression mo 1 to, yan, 2. Kasi intercool ka ng 2 to 4 on the pressure displacement diagram of figure 3 saves some work. If the processes are reversible, the saving is represented by the area in figure 3. Yeah. So figure 4 shows how compression with intercooling appear on the pressure enthalpy diagram of a refrigerant. So 1 to 2, then intercool to 2 to 4, then 4 to 5. Itong 1 to 3, ito yung walang intercooling. Process 1 to 3 and 4, 5 are on the lines of constant entropy, but process 2 to 3 falls on the flatter curve than 4 to 5. So between the same two pressure, therefore, process 4 to 5 shows a smaller increase in enthalpy. So, which indicate that less work is required than in 2 to 3. Another way of showing that the work of compression increases when the process moves out further into the superheat region is to examine the equation for work in reversible polytropic compression of a perfect gas, which is W is equal to negative the integral of B times dP is equal to N over N minus 1 times P1 B1 times 1 minus P2 over P1 exponent N minus 1 over N. Well, P is the pressure in Pascal, B is specific volume, cubic meter per kilogram, and is the polytropic exponent relating the pressure and a specific volume during compression. So PBN is equal to constant. So, and where subscript 1 refers to the entrance and 2 to the exit of the compressor. Between two given pressure, the work of compression is proportional to the specific volume of the entering gas. The specific volume at 2 in figure 4 is greater than it is at 4. So the work required for compressing from 2 to 4 to 3 is greater than in compressing 4 to 5. So intercooling in a refrigeration system can be accomplished with a water-cooled heat exchanger or by using refrigerant. Figure 5A and B. So ito yung compressor mo, tapos pasok sa intercooling sa the water. Ito B by liquid refrigerant. So this is from, ito yung compressor. Tapos, ito yung refrigerant po sa 2 plus gas. Ayan. May plus gas kasi, ito, may mix mo siya. So, lalabas yung gas mo doon. Dito applicable na yung plus gas tank. So, the water-cooled intercooler may be satisfactory for two-stage air compressor. But for refrigerant compression, the water is usually not cold enough. So the alternate method of figure 5B uses liquid refrigerant from the condenser to the intercooling. Discharge gas from the low stage compressor bubbles to the liquid in the refrigerant intercooler. Refrigerant leaves the intercooler as poor as saturated vapor. Intercooling with the liquid refrigerant will usually decrease the total power requirements when ammonia is the refrigerant, but not when refrigerant 12 or 22. So, yan ang ano niya. Pag in-examine mo yung ibang refrigerant. Pero in general, this will save power. Sample number 1. Calculate the power needed to compress 1.2 kg of ammonia from saturated vapor at 80 kilopascal to 1000 kilopascal. A, by single-stage compression, and B, by two-stage compression with intercooling by liquid refrigerant at 300 kilopascal. So given the mass of ammonia is 1.2 kg per second, and from saturated vapor at 80 kilopascal to 1000 kilopascal. Intercooling is at 300 kilopascal. Required the power by single-stage compression. B, the power by two-stage compression with intercooling. Solution. So single-stage compression is 1, 3, and 6. Properties of ammonia. Saturated point is at state point 1, saturated at 80 kilopascal. So H1 is 1410 kilojoule per kilogram. S1 is 6.2072 kilojoule per kilogram. At state point 3, 1000 kilopascal. So S3 is equal to S1. So this is superheated. So S3 is equal to 1800 kilojoule per kilogram. Now the power required is W times S3 minus H1. So again, W is M, yung mass. 1.2 times 18 minus 1410 or 468 kilowatt. Now, by two-stage compression with intercooling, from properties of ammonia at the state point 1, saturated at 80 kilopascal. So H1 again is 1410 kilojoule per kilogram. H sub 1 is 6.2072 kilojoule per kilogram. At the state point 2, 300 kilopascal, S2 is equal to S1 superheated vapor. S2 is equal to 1588 kilojoule per kilogram. Dito na siya may iba. 2, di ba? At the state point 4, saturated at 10 kilopascal, S4 is equal to 1450 kilojoule per kilogram. S4 is 5.7451. Then, at state point 5 na 1000 kilopascal, S5 is equal to S4. Separated vapor na yung sa 5. At this is H6 equal to 1628 kilojoule per kilogram. At the state point 6, again, for 1000 kilopascal saturated liquid, H6 is equal to 316. Kailangan natin yan. Dito wala pa. Work. Diba? So, kailangan na natin yung H6. Now, the flow rate of ammonia compressed in the high stage can be calculated making a heat and a mass balance about the intercooler as shown in figure 6. So, yung H1, H316 to 1450, ito yung mga enthalpies niya. This is 1.2. So, ilan to? So, from heat balance, so, W6, yung flow rate nito, W or mass. Dito ko na nabago, okay? Yung symbol. H6 plus W2 times H3 is equal to W4, H4. So W6 times 316 is plus 1.2 kilogram per second times 1588 kilojoule per kilogram is W4 times 1450 kilojoule per kilogram. So by mass balance, W6 plus W2 is equal to out, W4. So W6 is equal to 1.2 of W4. Solving simultaneously, ito, saka ito. So W4 is equal to 1.346 kg per second. Then power required is W2 times H2 minus H1 plus W4 times H5 minus H6 is 1.2 times 1588 minus 1410 plus 1.346 times 1628 minus 1450 is 453.2 kilowatt. So intercooling the ammonia with liquid refrigerant reduce the power requirement from 468 to 453.2. So a further benefit of intercooling the ammonia is that the discharge temperature from the high stage compression will be reduced from a value of 146, the temperature at 3 based on isentropic, to 77 C. Di bumaba. So the lower discharge temperature permits better lubrication and results in longer life of the compressor. There is an optimum pressure at which the intercooling should take place in ammonia, in an ammonia system. And the compression of air, where the intercooling is achieved by radiating heat to ambient or to cooling water. That intermediate pressure for minimum total power is PI is equal to the square root of PS as PD. PI is intercooler pressure, kilopascal. PS is the suction pressure of low stage compressor, kilopascal. P sub D is equal to discharge pressure of high compressor, kilopascal. So yun, intercooling. Pause muna tayo. Okay, one evaporator and one compressor system. Ito, one evaporator and one compressor. Sabihin, kahit may plus tank ka, isa lang siya. So magmi-mix lang siya dito. The plus tank and intercooler appear in most multi-pressure system and will now be examined in various compressor, evaporator, compressor. With one compressor and one evaporator, the plus tank may function as shown schematically in figure 7. A pressure-reducing valve throttles the plus gas from the intermediate pressure to evaporator pressure. So may throttling valve siya dyan. The throttling is necessary because there is no compressor available with a high suction pressure. So calculation would show that the plus tank does not improve the performance of the system. Pero yung temperature nga yung undischarged. The only reason for using the plus tank would be to keep the plus gas in the machine room rather than sending it to the evaporator. The plus gas in the evaporator tubes and long suction line does no refrigeration but does increase the pressure drop. The system is used infrequently. Next, two evaporators and one compressor. In many situations, one compressor serves two evaporator having different temperature requirements. Yan. Or different purpose. Ito different purpose to. An example is an industry which needs low temperature refrigeration for a process in which must provide air conditioning for some offices. So figure 8A shows one method of arranging the system and figure 8B shows the corresponding pressure enthalpy diagram. So yan, two compressor. One compressor and two evaporators with the air conditioning evaporator evaporating at negative C. So ito yung phase diagram. Same lang siya. Okay? Kaya nagdalawa lang yung evaporator mo. In figure 8A, the air conditioning evaporator operates at negative 10 C even though a higher temperature in this evaporator would cool the air sufficiently. Furthermore, difficulties may arise when an evaporator operates at an unnecessary low temperature. So an evaporator which cool air for air conditioning may colic frost, which block the air flow of air. An evaporator which chills a liquid may freeze the liquid. And an evaporator which cool air for a room where meat or product is stored may humidify the air so much that the products will be dehydrated. So to overcome drawbacks of the system, in figure 8, a revision may be made as shown in figure 9. So a pressure reducing valve installed after the high temperature evaporator regulates the pressure and maintains temperature in the air conditioning evaporator of 5C, for example. Ayan. So ito magiging diagram niya. So magkaiba na yung pressure at temperature. Okay, ito nga yun. So this is the pressure and enthalpy diagram. So process niya, so paggawa ng, ng PS chart. So mag-umpisa ka sa condenser, siyempre yung 2 to 3. Yung 3 to 4, dito nag-separate sa 5C. The lower temperature or pressure is negative 10C. Okay, ito yung saturation yan, sinasabi dyan. Yan, so nag-separate siya dito. So ito yung throttling valve, tapos dito sa 4 throttling valve siya. Wala siyang blast tank, kaya diretso siya. So dito, Sa 5, itong 5 to 6, ito yung ano ng pressure reducing valve. Same siya ng ano siya, constant enthalpy rin ng expansion valve. So, yan. Tapos dito, yung compressor mo, evaporate 8. Tapos 8 and 6, magko-combine siya. So, sa 1 siya. Then, punta sa 2. So, yan. Okay? Ganyan paggawa sa PS charts para maano mo yung calculation. So, it balance. Now, figure 9B shows the corresponding pressure. Ito nga, enthalpy diagram. Differences in performance between the systems 8A and 9A are as follows. In figure system of 9A, the refrigerating effect and the high temperature evaporator is greater than it is in the system of figure 8A. So, this is an advantage for the system of figure 9A. To counterbalance this advantage, the compression in figure 9B occurs further out in the superheat region than in figure 8B. The system of figure 9A therefore demands more work per kilowatt of refrigerant. So from power standpoint, the system are practically a stand-up. But for proper operation of high temperature evaporator, the system of figure 9A is preferred. High temperature. Now, two-stage compression with intercooling of removal of flash gas is often the ideal way to serve one low temperature evaporator sa isang system yun. This system requires less power than with a single compressor, and often the saving in power will justify the cost of extra equipment. So dito sa lower side, pwede ka dito, flash gas. Example number 2. So for 2 compressor with 1 evaporator. Example number 2. Calculate the power required by 2 compressor in an ammonia system which serves 250 kilowatt evaporator at negative 25 C. So the system uses two-stage compression with intercooling and removal of gas. So yan. So the condensing temperature is 35 C ito. Ayan yung drawing nyo. So sa problem ito, wala yung drawing. So ikaw concept ng conceptualize ng drawing. Okay? Ayan naman sa mga books. So high stage compression, yan. Compress. So this is the pH chart. 1 to 2, nag-compress. Then 3 to 4, 5, 6, nag-separate siya. 6, so 7 dito. Then yung 3, nag-separate siya, di ba yung 3? So yan. Compress naman doon. Tapos, to. So ang ano to, 2 and 2 is papasok siya dito sa sa flash tank, intercooler and flash tank. So magkukul siya. Mag-mix. So pasok yung 6. So ito, ang labas nito is saturated 2 to 3. Okay. So, given 2 compressors ammonia system 250 kilowatt evaporator at negative 25 C with intercooling and removal of flash gas. Condensing temperature is 35 C. The power required by the 2 compressors. Yung total. Solution. First, sketch the schematic diagram of the system figure 10A. Yan. So, kaya gagawa ka yan. And the corresponding pressure enthalpy diagram. The functions of the intercooler and flash tank are combined in one vessel. Determine the intermediate pressure for optimum economy. So, walang given na pressure na intermediate. So, ikaw gagawa. So, wait muna. Tapos yung symbol natin. So, ito. So, P sub S, saturation pressure at negative 25 C is 152 kilopascal. S is the suction. Ito. Ng P sub D, ito yung here discharge. Saturation pressure at 35 C is 1352 kilopascal. So, intercooling pressure is the square root of PS and PD is equal to the square root of 152 times 1352 is 453 kilopascal. Take note that these are absolute pressure. So, the enthalpies at all points can now be determined from ammonia table of properties. So, at state point 1, so dito, H1 is equal to Hg at negative 25 C or 1430 kilojoule per kilogram. S sub 1 is 5.9813 kilojoule per kilogram Kelvin. At the state 2, the entropy is constant 1 to 2. H2 is equal to H at 453 kilopascal after compression. Isentropic compression is 1573 kilojoule per kilogram. So, ang pressure mo is 453. At state 3, this is Hg at 453 kilopascal. And St is equal to 5.6001 kilojoule per kilogram. So, at state point 4, S4 is equal to S3. H4 is equal to S at 1352 kilopascal after isentropic compression or 1620 kilojoule per kilogram. Oh, oops. Tayo natin na slideshow. So at the state point 5, so this is HF at 35 C or 366 kilojoule per kilogram. At the state point 6, H6 is equal to H5. At the state point 7, so this is H sub F at 453 kilopascal or 202 kilojoule per kilogram. At 8, this H8 is equal to H7. So mass rate of flow, so gawa tayo ng heat balance about the evaporator. Ito. So this is M1 is equal to QA over H1 minus H8 or 250 kilowatt yan, di ba? Over 1430 minus 202 is 0.204. Take note that M1 is equal to M2 is equal to M7 and M8. Iyan ang nag-circulate dito. Ano yung nag-circulate sa taas naman? Yeah. Heat balance, heat and mass balance about the intercooler. So M2, pumasok siya, plus M6, pumasok siya, H6. So is equal to M7, lumabas. H7 and M3, H3. So yan. M6 is equal to M3 kasi ito nga M2 is equal to 7. So 0.204 times 1573 plus M3 times 366 is equal to 0.204 times 202 plus M3 times 1463. So M3 is equal to 0.255 kilogram per second. This is also M6. And also M4, also M5. Now, for low stage power, M1, H2 minus H1 is 0.204 times 1570 minus 1.30 is 29.2 kilowatts. High stage power is 0.255 times 1620 minus 1460 is 40 kilowatt. So the total power is 29.2 plus 40 is equal to 69.2 kilowatt. So this is the total power required by two compressor. Next is two compressors and two evaporator. So, ang figure na andito to evaporator, to compressor. So, the system which has two evaporator operating at different temperature is common in industrial refrigeration. A frozen food plants may require two evaporator at different temperature, one at negative 40 C to quick freeze the food and the other negative 25 C to hold the food after it is processed. Evaporators at two different temperature can be handled efficiently by two-stage system which employs intercooling and removal of flash gas. Dumadami ng components. So example number 3, in an ammonia system, one evaporator is to provide 180 kilowatt of refrigeration at negative 30 C and another evaporator is to provide 200 kilowatt at 5 C. The system uses two-stage compression with intercooling and is arranged as in figure 11-A is given. The condensing temperature is 40 C. Calculate the power required by the compressors total. Okay, given 180 kilowatt of refrigeration at negative 30 C, 200 kilowatt of refrigeration at 5 C, condensing temperature is 40 C. Required is power required by the compressor. Solution: sketch the pressure enthalpy diagram of the cycle as in figure 11B. So ito lang sketch niya. 1, 2, 3, 4. So ito diba yung sa 6. So ang intercooling mo, ito, same siya ng 5 kasi dito sa nag-separate, diba? So, kaya itong 5 and 6, isa dyan sa evaporator, dumiretso. So, isa sa intercooling sa plus tank. So, 3 and 7, mag-iwalay. So, kaya tingnan niyo mabuti yung diagram. Yan. So, the discharge pressure of the low stage compressor and the suction pressure of the high stage compressor are the same as the pressure in 5C evaporator. Enthalpies at state 1, state points at state 1, state point 1, H1 is equal to Hg at negative 30 C versus 1423 kJ per kilogram. S1 is equal to Hg at negative 30 C is 6.0366 kJ per kilogram. At the state point 2, this is isentropic 1 to 2, H2 is equal to H at 517 kilopascal after isentropic compression or 1630 kJ per kilogram. At state point 3, H3 is equal to Hg at 5C or 1467 kJ per kilogram. S3 is equal to Hg at 5C is 5.5545 kJ per kilogram. At the state point 4, H4 is equal to H at 1557 kilopascal after isentropic compression or 1652 kJ per kilogram. At the state point 5, H5 is equal to SF at 40 C or 390.6 kJ per kilogram. I-change ko lang ito. Then at state point 6, ito yung 6. S6 is equal to H5, 390 kJ per kilogram. At state point 7, so H7 is SF at 5C to 30 kJ per kilogram. At 8, H8 is equal to H7. So the mass flow rate of flow is M1 is equal to QA1 over S1 minus S8 is equal to 180 kilowatt over 1423 minus 223 is 0.15 kilogram per second. Ba, yung M1. So ito yung M1. So M1 mo is yung dumaan sa 180 kilowatt. So M7 is equal to M8 is equal to M2 is equal to M1. Diba? Ito. So ano naman yung sa 200 kilowatt? Okay, wait. Probably the simplest way to calculate the mass rate of flow handled by the high stage compressor is to make a heat balance about both the high temperature evaporator and the intercooler as shown in figure 12. Ito. Buuhin mo to para makuha mo yung flow rate nito sa kayan. So heat balance M5 H5 plus QA2 plus M2 H2 is equal to M3 H3 plus M7 H7. So mas balance, M2 is equal to M7, siyempre 0.15. Therefore, M5 is equal to M3. Combining M3 times 390.6 enthalpy na plus 200 plus 0.15 times 1630 is M3 times 1467 plus 0.15 times 223. So M3 is 0.382 kilogram per second. Malaki. The power required by the compressor can now be, so di natin kailangan yung dumaan dito yan lang. Binuo natin to, binuo. So the power required by the compressor can now be calculated. So low stage is M3 times S4 minus S3 is 0.15 times 160 so minus 1423 is 31.1 kilowatt. high stage power is M1 times S2 minus S1 is 0.382 times 1625 minus 1467 is 60.4 kilowatt. Text. Then auxiliary equipment. Modifications are sometimes made in the equipment for intercooling and removal of gas. If the temperature of the discharge from the low stage compressor is sufficiently high, a water-cooled heat exchanger may remove some of the heat from the discharge gas before it flows into the main intercooler. Mga dagdag. A device which gives the same result as flash gas removal is called the liquid subcooler. So, ayan. Figure 13. Sitang itatawag na liquid subcooler. Subcooler yung ano mo. Subcool mo yung liquid na galing sa condenser through dito sa flash gas. It cools the liquid refrigerant by evaporating a small fraction of the liquid. Compared with direct contact flash tank, the subcooler cannot cool the liquid to quite as a low temperature. On the other hand, the subcooler maintains the liquid at a high pressure. If the liquid must flow through a long line before it reaches the expansion valve, there is less possibility that the pressure drop in the line will flush the liquid to vapor and thus restrict the flow to the expansion valve. Compound compressor. In compound reciprocating compressor, 4 cylinders of a 6-cylinder compressor might perform the low stage compression and the remaining 2 cylinder would accomplish the high stage compression. Ibig sabihin, dalawang compressor na isang case lang, isang package lang. In a compound screw compressor, the entrance of gas at the intermediate pressure takes place partway along the compression process. Okay. Liquid recirculation system. Ito. So, schematic diagram of liquid recirculation is shown in figure 14. So, instead na ito evaporator, so gumawa siya ng isa pang separator tank. So, ito yung tinatawag na recirculation. Recirculate niya yung liquid. Lahat ng liquid. Ito, kasi liquid and vapor, tatanggalin niya yung vapor, punta doon, yung liquid naman dito. A liquid pump delivers the low temperature liquid to the evaporator, which can be regulated by thermostatically controlled solenoid valve. Since the pump supplies several times as much refrigerant to the evaporator as can be evaporated, some liquid washes out of the evaporator and returns to the separator. Yun. Okay. Dami pang iba-ibang system. Summary, in multi-pressure system, the removal and the compression of flash gas before complete expansion decrease the power required by the compressor. Intercooling between stages of compression reduces the power requirement, at least when ammonia is the refrigerant. Yan, common. Intercooling decreases the discharge temperature of the refrigerant from the high stage compressor. High discharge temperature cause oil carbonization, sticky compressor valve, and lubrication difficulties and reciprocating compressor. So, ano sa example natin, yung alin doon, yung bumaba yung discharge temperature. So, okay. So, ito yung sa internet, mga diagram. Ayan, dami intermediate pressure vapor refrigerant. Ang dami siya. Okay. Liquid separator. So, lahat yan gagawa mo ng pH charge. So, analysis. Okay. Thank you very much.